All right, time for a discussion of the structure of atoms, starting with electrons. This again largely originates in a historical discussion. Back in the 1800s, a fellow by the name of J.J. Thomson was experimenting with cathode ray tubes. Ironically, cathode ray tubes are exactly what our first television sets used, and computers too, but now they've largely been replaced by flat screen devices. Most of your instructors grew up on cathode ray type devices. And cathode ray type tubes have been used for other things long before that. And what Thomson proposed was that cathode rays must consist of tiny negatively charged particles that we now describe as electrons. The symbol for an electron will commonly be shown like this. We like abbreviations. And so what do we mean by a cathode ray tube? Well, they knew about cathodes and anodes. They weren't quite sure what was all about them, but they had these names historically. And a cathode and an anode are the opposite ends of this device. And the cathode ray is going from a slit, and you can visibly see it passing through this tube, and it's got visible because of the phosphorescent background, and ordinarily travels in a straight line. And so a cathode ray was used for various things that we wouldn't begin to wonder about in the 21st century. Well, they figured out that you could deflect a cathode ray by using a magnet. In other words, it's quite visible here because of the phosphorescent background. The electrons were moving straight, but then they're being pushed upward, or pulled, if you will, by the magnet. And so there's got to be something about opposites being attracted that just allows that pushes the path of these the cathode ray and bends it, because they're negatively charged, and they must be very tiny that they're in this particle, in this cathode ray. So where do these electrons fit into the whole thing? This was a very revolutionary discovery in the 1800s or in early 1900s. The second piece of information about electrons was attributed to an experiment by Millikan. And Millikan did this very interesting experiment, and we wonder how they ever come up with these ideas in the 1900s, but go for it. Good for them. So this experiment is shown in this complex diagram, and let's see if we can make sense of it. So on the right side of this big box is a little bulb that is going to take and push air past this oil solution, and it's going to go into the box and comes out as a fine drop, a spray of fine droplets. The droplets are going to go through a pinhole. The pinhole is in this little platform in the box, and underneath the pinhole, X-rays are being projected or shot through, or whatever you want to call it, passing through a hole in the box. The X-rays are going to go in there and impact and affect these oil droplets going through. Well, this platform in here, what are they? Well, there's two of them. They're electrically charged brass plates. One of them is positively charged, and one of them is negatively charged. They knew a lot of things about electricity that 21st century folks didn't even wonder about. And as they do this, the X-rays are going to impact the little oil droplets, and they're going to be suspended in the space as they travel between the positive and negatively charged brass plates. Well, what did they figure out? They were able to observe the droplet as it passed between the charged plates. Well, what happens? The oil droplets were allowed to reach their terminal velocity, and they were able to suspend them between the two plates because of there being a charge. The falling oil droplets are given a negative charge by the X-rays. So the X-rays impact the droplets to give them a resulting negative charge. And if you adjust the current accurately between the two plates, then they were able to suspend them exactly in the middle between these two plates. The conclusion is then the charge on the drop is calculated based on the mass of the drop and the voltage on the plates. Now, this is far more complex than a calculation we're going to hope to do in our course, but they were able to use some sophistication to figure out the charge on the drop based on the mass of the drop and the voltage of the plate. As a consequence, they were able to come up with the mass of each drop having multiples of charges of electrons, and the mass of one electron was the least common multiple of all of these calculated values. Interesting. And they're adding electrons to the oil droplets and then suspending them between plates. Wow. Interesting and sophisticated. Further discovery about things happening in atoms are attributed to Rutherford, and Ernst Rutherford, who lived before and after the turn of the century into the 20th century, before and after 1900. He directed a beam of alpha particles at a thin gold foil. And why would you choose this? Well, you were trying to project this alpha particle beam coming from a radioactive sample. The radioactive sample of alpha particles, they were beginning to understand alpha particles gradually, and they wanted to see what would happen if it went directed at something that's really thin. Now, gold is a metal, and you can pound it into a thin sheet, and therefore they put it into a thin sheet as possible and found out what would happen if these alpha particles were directed at that foil. And he found out that most of the alpha particles went straight on through from the source and were detected on a detector film behind the gold foil. But there was a circular kind of screen, it's a zinc sulfide screen, you can see that here, that was able to detect where the alpha particles might be impacting, whether they went straight through the foil or somewhere different, somewhere else in the perimeter around that foil. So some of them were deflected. And that was highly unexpected because they sort of figured that the alpha particles would just bounce right off the solid gold. It's metal after all, right? Well, a very few of the particles, very small number, about 1 in 20,000 were deflected at an angle and actually bounced back towards the particle source. So some of these went kind of towards the source, some of them went in funny directions. This experiment was done around 1910. And this scattering experiment provided some great insights to the nature of the atom. He explained this deflection in this way. He proposed that a metal atom like gold must be nearly entirely empty space, and that the mass with charges was concentrated in a tiny central core that he called a nucleus. So the picture at the right here, the diagram from your text, gives you the idea of what's happening. The alpha particles are shown at the left here, and if they went in just the right way across the very thin foil, they would go straight through. If they went in just a different way and they didn't go straight through, sometimes they would come in close contact with something in the nucleus, and if they have the same charge, it would deflect it because the alpha particle has a positive charge. And if the nucleus has a positive charge, that would be deflecting. Like charges repel, repelling it to go a different direction rather than straight through, in this example right here. And then the last one down here at the bottom, if the alpha particle went exactly the right place, the exact correct angle, it might actually hit that central thing with a positive charge and be totally deflected back towards the source. And so most of the particles went straight through because it's mostly empty space, But only when they hit a nucleus are the particles deflected to go some other direction, the alpha particles. So this gave a big insight to the nature of an atom, mostly empty space and having mass concentrated in the middle. We call it a nucleus. So most of the mass is there. Further things to discuss about the nature of the atom with protons and neutrons has to do with size. We all know that things that are subatomic or molecular in dimension, we cannot see them as atoms and molecules unless you have high-tech electron microscopes and such, and so it's hard for us to imagine how the size of an atom or molecule might be. So here's a really good analogy, and this one's from your text as well, but it's a perfectly good one. If you took a pea, an ordinary garden pea, and dropped it in the middle of a large sports stadium, the pea is to the stadium as the nucleus is to the entire atom. In other words, the nucleus is the center, and the stadium is the volume of the entire atom, including the electrons. And the whole thing where the electrons occur is huge compared to this central nucleus that has the protons and neutrons. That was things that Rutherford's experiments helped to show. So let's talk more about the protons and neutrons and the electrons that are in this atom with a very, very teeny tiny nucleus and a large volume of space around it where the electrons are occurring. So let's make that statement. The volume where electrons are found is equivalent to the stadium size compared to the nucleus being a little tiny p. Now, the electron, proton, and neutron have been characterized to their masses and their atomic mass units, is the middle column, either in grams or in atomic mass units, and by their charge. The charge of the electron was indeed highly closely characterized by Millikan's experiment, oil drop experiment. And the first thing you notice that is, if you're looking at electrons, protons, and neutrons, that which is in the nucleus is the protons and the neutrons. And the mass of the atom is largely in the nucleus. Notice these numbers are much bigger. 10 to the minus 24 is a lot more than 10 to the minus 28. So the mass of the atom is largely found in the nucleus. What else does this information show us? The charge of the proton is opposite in sign but equal to that of the electron. So they have opposite charges, and they're just defined as a charge of 1. So one's plus, one's minus. The proton is plus, and the electron is negative. Now, the proton has a lot more mass than the electron, but they're opposite and equal in charge. All right, important things to know about atoms. One more. So here's another way of thinking about this thing, the structure of the atom, where the protons, neutrons, and things occur. The approximately 10 to the minus 10 meters, which is pretty tiny, it's less a tenth of a nanometer, 0.1 nanometer, is the volume occupied by charged electrons. And 10 to the minus 15th is 1 femtometer, that's pretty small, is the volume of the diameter of the nucleus. So the electrons occupy a volume 10 to the 5th, which would be 100,000 times bigger than the nucleus. And so 10 to the 5th bigger than the nucleus. The protons and neutrons in the nucleus take up very little volume, but can essentially contain all of the atom's mass. Kind of mind-bending. I apologize if you are red-green colorblind, because this won't make any sense to you, but the protons are shown in red here. These are representing protons. And the neutrons, which have no charge, are the other remaining green spheres in this diagram. All right, so here's things that help you understand the structure of the atom. I hope you find that helpful. End of recording.